In this video, you'll learn about scalability and high availability. In modern computing environments, scalability and high availability are crucial aspects of building robust and reliable backend systems. This chapter explores various strategies and architectures for achieving scalability and high availability in backend development, along with best practices for disaster recovery planning and leveraging cloud computing platforms. 12.1 Scaling Strategies, e.g., vertical scaling, horizontal scaling. In the realm of backend development, scaling strategies play a pivotal role in ensuring that systems can accommodate growing workloads and increasing user demands. Two primary scaling strategies commonly employed are vertical scaling and horizontal scaling. Each approach offers unique advantages and considerations, catering to different use cases and architectural requirements. Vertical scaling, also known as scaling up, involves increasing the capacity of individual resources within a single server or instance. This approach focuses on enhancing the capabilities of existing hardware components, such as CPUs, memory, or storage, to handle greater workloads. 1. Hardware upgrades. Vertical scaling typically involves upgrading hardware components to more powerful or higher capacity versions. For example, upgrading from a dual-core CPU to a quad-core CPU, or increasing RAM from 8 GB to 16 GB. 2. Ease of implementation. One of the advantages of vertical scaling is its relative simplicity in implementation. Hardware upgrades can often be performed without significant changes to software configurations or architectural designs. 3. Cost considerations. While vertical scaling offers immediate performance boosts, it may become cost-prohibitive as system requirements continue to grow. Upgrading to high-end hardware components can incur substantial expenses, especially for large-scale deployments. 4. Single point of failure. A potential drawback of vertical scaling is the increased risk of a single point of failure. Since all resources are concentrated within a single server or instance, any hardware failures could lead to service disruptions for the entire system. Horizontal scaling. Horizontal scaling, also known as scaling out, involves adding more resources, such as servers or instances, to distribute the workload across multiple machines. This approach emphasizes scalability through parallelization and redundancy. 1. Distributed architecture. Horizontal scaling relies on a distributed architecture where workloads are distributed across multiple servers or instances. This distributed approach enables better fault tolerance and resilience against hardware failures. 2. Elasticity and flexibility. Horizontal scaling offers greater elasticity and flexibility, allowing systems to scale dynamically in response to changing demands. Additional servers or instances can be added or removed as needed, providing a more cost-effective and efficient scaling solution. 3. Load balancing. Effective load balancing is essential for ensuring even distribution of workloads across multiple servers. Load balancers distribute incoming requests or traffic across back-end servers based on predefined algorithms, such as round-robin or least connections. 4. Complexity and coordination. While horizontal scaling offers scalability and fault tolerance, it also introduces complexities in terms of coordination and synchronization. Managing distributed systems requires careful orchestration to ensure consistent performance and data integrity. 5. State management. Handling stateful components, such as session data or database connections, in a horizontally scaled environment can pose challenges. Implementing strategies for state management, such as session affinity or distributed caching, is crucial for maintaining application consistency. In conclusion, both vertical scaling and horizontal scaling are viable strategies for achieving scalability in backend development, each with its own strengths and considerations. Vertical scaling offers simplicity and immediate performance gains, but may encounter limitations in terms of cost and scalability. Horizontal scaling, on the other hand, provides greater flexibility, fault tolerance, and scalability, albeit with increased complexity and coordination requirements. Ultimately, the choice between vertical and horizontal scaling depends on factors such as application requirements, budget constraints, and future growth projections. By carefully evaluating these factors and implementing appropriate scaling strategies, organizations can build resilient and scalable backend systems capable of meeting evolving demands and ensuring optimal performance. 12.2 High availability architectures, e.g. failover, redundancy. High availability HA architectures are fundamental to the resilience and reliability of backend systems, ensuring uninterrupted service delivery even in the face of hardware failures, network issues, or other disruptions. This segment delves into key concepts and strategies employed in high availability architectures, including failover mechanisms, redundancy strategies, and their implementations. Failover mechanisms. Failover is a critical component of high availability architectures, designed to automatically switch to a backup system or component in the event of a failure, thereby minimizing downtime and maintaining service continuity. 1. Active-passive failover. In an active-passive failover setup, one system active handles production traffic, while the other, passive, remains idle as a standby. If the active system fails, the passive system takes over to resume operations. This approach ensures redundancy, but may result in underutilization of resources during normal operation. 2. Active-active failover. Active-active failover involves multiple systems simultaneously handling production traffic, with each system capable of serving requests independently. In the event of a failure, traffic is automatically rerouted to the remaining operational systems, ensuring continuous service availability. This approach maximizes resource utilization, but requires careful load balancing and synchronization mechanisms. 3. Heartbeat monitoring. Failover mechanisms typically rely on heartbeat monitoring to detect system failures. Heartbeat signals are exchanged between systems at regular intervals, indicating their operational status. If a system fails to send or receive heartbeat signals within a specified time frame, it is considered offline, triggering failover procedures. 4. Quorum-based failover. Quorum-based failover mechanisms require a minimum number of systems or nodes to be operational to maintain service availability. This ensures that failover actions are only initiated when a sufficient number of systems agree on the need for failover, preventing split-brain scenarios where multiple systems attempt to take over simultaneously. Redundancy strategies. Redundancy plays a crucial role in high availability architectures, enabling systems to withstand failures by providing backup resources or components. 1. Hardware redundancy. Hardware redundancy involves duplicating critical components such as servers, storage devices, or networking equipment to ensure that a backup resource is available in case of failure. Redundant hardware configurations such as RAID arrays or hot swappable components help mitigate the impact of hardware failures on system availability. 2. Data redundancy. Data redundancy ensures that critical data is replicated across multiple storage devices or locations to prevent data loss and facilitate data recovery in the event of storage failures or disasters. Techniques like data mirroring, replication, and distributed storage systems enhance data resilience and availability. 3. Network redundancy. Network redundancy involves deploying redundant network paths, links, or devices to eliminate single points of failure and maintain network connectivity even during network outages or failures. Redundant network infrastructure, such as dual-homed connections or mesh topologies, enhances network resilience and fault tolerance. 4. Service redundancy. Service redundancy entails deploying duplicate instances of critical services or applications across multiple servers or data centers to ensure continuous service availability. Load balancers, clustering, and auto-scaling mechanisms help distribute incoming requests and ensure fault tolerance by redirecting traffic to healthy instances. Implementation considerations. Implementing high availability architectures requires careful planning, design, and configuration to ensure effectiveness and reliability. 1. Failure detection and recovery. Effective failure detection mechanisms, automated failover procedures, and robust recovery processes are essential for minimizing downtime and maintaining service continuity. 2. Scalability and elasticity. High availability architectures should be designed to scale dynamically to accommodate fluctuating workloads and changing demands without compromising performance or reliability. 3. Geographic redundancy. Geographic redundancy involves deploying redundant systems or data centers in geographically diverse locations to mitigate the impact of regional disasters or infrastructure failures. 4. Testing and simulation. Regular testing, simulation, and disaster recovery drills are critical for validating the effectiveness of high-availability architectures and identifying potential weaknesses or vulnerabilities. In conclusion, high-availability architectures play a vital role in ensuring the reliability, resilience, and continuity of back-end systems, particularly in mission-critical applications and services. By implementing failover mechanisms, redundancy strategies, and robust fault tolerance mechanisms, organizations can minimize downtime, mitigate risks, and maintain seamless service delivery even in the face of adverse conditions or unexpected failures. However, achieving high availability requires a holistic approach encompassing careful design, rigorous testing, and continuous optimization to address evolving challenges and meet the demands of modern digital environments. Disaster recovery planning. Disaster recovery planning, DRP, is a critical component of high availability and resilience strategies for back-end systems. It involves the development and implementation of procedures and processes to restore operations and data integrity in the event of a disaster or disruptive event. In this extended discussion, we'll delve deeper into the key aspects of disaster recovery planning, including its importance, essential components, best practices, and challenges. Importance of disaster recovery planning. Disasters, whether natural or man-made, can have devastating consequences for organizations, resulting in data loss, downtime, financial losses, and reputational damage. Disaster recovery planning is essential for the following reasons. 1. Minimizing downtime. A well-defined disaster recovery plan helps organizations minimize downtime by enabling swift recovery and restoration of critical systems and services. 2. Protecting data. DRP ensures the integrity and availability of data by implementing backup and recovery mechanisms to prevent data loss and facilitate data restoration in the event of a disaster. 3. Ensuring business continuity. By enabling organizations to quickly resume operations following a disaster, DRP helps maintain business continuity, safeguarding revenue streams, customer trust, and brand reputation. 4. Compliance and regulatory requirements. Many industries are subject to regulatory mandates that require organizations to have robust disaster recovery plans to protect sensitive data and ensure regulatory compliance. 5. Risk mitigation. DRP helps mitigate the risks associated with unforeseen events, such as natural disasters, cyber attacks, hardware failures, or human errors, by providing a structured framework for response and recovery. Essential components of disaster recovery planning. An effective disaster recovery plan typically includes the following key components. 1. Risk assessment and business impact analysis. Conducting a comprehensive risk assessment and business impact analysis helps identify potential threats, vulnerabilities, and the potential impact of disruptions on business operations. 2. Recovery objectives and priorities. Defining recovery objectives such as recovery time objectives, RTOs, and recovery point objectives, RPOs, helps prioritize critical systems and data for recovery. 3. Backup and data protection strategies. Implementing robust backup and data protection strategies, including regular backups, offsite storage, and encryption, ensures the availability and integrity of critical data for recovery. 4. Disaster recovery procedures. Documenting detailed procedures and workflows for disaster recovery, including roles and responsibilities, escalation paths, and communication protocols, streamlines the recovery process and ensures consistency and effectiveness. 5. Testing and training. Regular testing and training exercises, such as tabletop simulations and full-scale drills, help validate the effectiveness of the disaster recovery plan, identify gaps or weaknesses, and familiarize stakeholders with their roles and responsibilities during a disaster. 6. Continuous improvement and updates. Disaster recovery planning is an ongoing process that requires regular review, updates, and refinement to adapt to changing business needs, technological advancements, and emerging threats. Best practices for disaster recovery planning. To ensure the effectiveness of disaster recovery planning, organizations should adhere to the following best practices. 1. Engage stakeholders. Involve key stakeholders from across the organization, including IT teams, business units, senior management, and external partners, in the planning and implementation of the disaster recovery plan. 2. Document and communicate. Document the disaster recovery plan thoroughly, including procedures, contact information, recovery strategies, and dependencies. Ensure that all stakeholders are aware of their roles and responsibilities and have access to the relevant documentation. 3. Regular testing and validation. Conduct regular testing and validation of the disaster recovery plan to identify weaknesses, assess readiness, and improve response capabilities. Simulate various disaster scenarios to ensure preparedness for different contingencies. 4. Automate where possible. Leverage automation tools and technologies to streamline backup, recovery, and failover processes, reducing manual intervention and accelerating response times during a disaster. 5. Ensure redundancy and resilience. Implement redundant systems, infrastructure, and data replication mechanisms to enhance resilience and minimize single points of failure. Consider leveraging cloud-based services and distributed architectures for added redundancy and scalability. 6. Monitor and analyze. Implement robust monitoring and analytics tools to continuously monitor system health, performance, and security posture. Proactively identify anomalies, potential issues, or emerging threats that could impact disaster recovery efforts. Despite the benefits of disaster recovery planning, organizations may encounter various challenges in its implementation. Cost and resource constraints. Developing and maintaining a comprehensive disaster recovery plan requires significant financial investment, resources, and expertise, which may pose challenges for smaller organizations with limited budgets and IT capabilities. Complexity and dependencies. Modern IT environments are increasingly complex with interconnected systems, applications, and dependencies. Managing these complexities and ensuring seamless integration between different components can be challenging during disaster recovery efforts. Human error and compliance risks. Human error remains a significant risk factor in disaster recovery planning, as misconfigurations, procedural errors, or inadequate training can undermine the effectiveness of recovery efforts. Compliance with regulatory requirements, such as data protection laws and industry standards, adds another layer of complexity and accountability. Evolution of threat landscape. The evolving threat landscape, characterized by cyber attacks, ransomware, and other malicious activities, presents ongoing challenges for disaster recovery planning. Organizations must continuously adapt their strategies to address emerging threats and vulnerabilities effectively. Disaster recovery planning is a critical component of organizational resilience, ensuring the availability, integrity, and continuity of business operations in the face of disruptions and disasters. By prioritizing risk assessment, robust recovery strategies, regular testing, and continuous improvement, organizations can mitigate the impact of disasters, protect critical assets, and maintain business continuity even in the most challenging circumstances. Cloud computing platforms, such as Amazon Web Services, AWS, and Microsoft Azure, have revolutionized the way organizations build, deploy, and manage their IT infrastructure and applications. In this extended discussion, we'll explore the key features, benefits, use cases, and considerations of cloud computing platforms, with a focus on AWS and Azure. Introduction to cloud computing platforms. Cloud computing platforms provide on-demand access to a wide range of computing resources, including virtual servers, storage, databases, networking, and other services over the internet. These platforms enable organizations to scale their IT infrastructure dynamically, optimize costs, improve agility, and accelerate innovation. Scalability. Cloud computing platforms offer virtually unlimited scalability, allowing organizations to scale resources up or down dynamically based on demand. This elasticity enables businesses to handle fluctuations in workload and accommodate growth without upfront investment in physical infrastructure. Flexibility and customization. Cloud platforms provide a diverse range of services and configurations, allowing organizations to tailor their infrastructure and applications to meet specific requirements. Whether it's compute instances, storage options, or networking configurations, cloud providers offer a variety of choices to suit different use cases. High availability and reliability. Cloud platforms are built on redundant and geographically distributed infrastructure, ensuring high availability and reliability for critical applications and services. Providers offer service-level agreements, SLAs, guaranteeing uptime and performance, with built-in redundancy and failover mechanisms. Security and compliance. Cloud providers implement robust security measures to protect customer data, including encryption, access controls, and compliance certifications. Additionally, cloud platforms offer a range of compliance features and certifications to meet regulatory requirements in various industries and regions. Pay-as-you-go pricing. Cloud computing platforms operate on a pay-as-you-go pricing model, allowing organizations to pay only for the resources they consume. This cost-effective approach eliminates the need for upfront capital investment and provides greater flexibility in managing IT budgets. AWS versus Azure, a comparison. Market dominance. AWS is the market leader in cloud computing, with a broad portfolio of services and a large customer base across industries. Azure, backed by Microsoft's extensive enterprise presence, is also a major player and has gained significant market share in recent years. Service offerings. Both AWS and Azure offer a wide range of services, including compute, storage, networking, databases, AI, ML, IoT, and more. AWS has a larger number of services and features, while Azure provides seamless integration with Microsoft products and services. Global infrastructure. AWS has a more extensive global infrastructure, with data centers in more regions compared to Azure. However, Azure is rapidly expanding its global footprint and has a presence in key regions worldwide. Pricing and cost management. AWS and Azure have similar pricing models, but the cost structure and pricing details may vary for specific services. Organizations should carefully evaluate pricing options, discounts, and cost management tools to optimize their cloud spending. Integration and ecosystem. Azure offers tight integration with Microsoft's ecosystem, including Windows Server, Active Directory, Office 365, and Visual Studio. AWS has a broader partner ecosystem and extensive third-party integrations, making it suitable for diverse use cases and industries. Use cases and applications. Cloud computing platforms are used across various industries and sectors for a wide range of applications, including web hosting and application development. Organizations use cloud platforms to host websites, web applications, and APIs, leveraging scalable compute and storage resources to handle fluctuating traffic and workloads. Data analytics and big data. Cloud platforms provide powerful analytics and big data processing capabilities, enabling organizations to analyze large data sets, derive insights, and make data-driven decisions. Enterprise applications. Enterprises migrate their on-premises enterprise applications, such as ERP, CRM, and HR systems, to the cloud to improve scalability, agility, and cost efficiency. DevOps and continuous integration, continuous deployment, CI/CD. Cloud platforms support DevOps practices, enabling organizations to automate software development, testing, deployment, and monitoring processes for faster delivery and improved collaboration. IoT and edge computing. Cloud providers offer IoT and edge computing services for managing and processing data from connected devices and sensors, enabling real-time insights, predictive maintenance, and automation. Considerations and challenges. While cloud computing platforms offer numerous benefits, organizations should consider the following factors and challenges. Data security and compliance. Organizations must address data security, privacy, and compliance requirements when migrating sensitive data and workloads to the cloud. Implementing robust security controls, encryption, and compliance measures is essential to mitigate risks. Vendor lock-in. Organizations should be aware of the potential for vendor lock-in when relying heavily on a single cloud provider. Adopting a multi-cloud or hybrid cloud strategy can help mitigate the risk of dependency on a single vendor. Performance and latency. Considerations such as network latency, data transfer speeds, and geographic proximity to cloud data centers can impact application performance and user experience. Organizations should assess these factors when designing their cloud architecture. Cost management and optimization. While cloud computing offers cost advantages, organizations must manage and optimize their cloud spending to avoid unexpected costs and overspending. Implementing cost monitoring, optimization strategies, and reserved instances can help control costs effectively. Skills and training. Cloud adoption requires skilled professionals capable of designing, deploying, and managing cloud infrastructure and applications. Organizations should invest in training and upskilling their IT teams to ensure successful cloud adoption and operation. Cloud computing platforms such as AWS and Azure have transformed the way organizations build, deploy, and manage IT infrastructure and applications. By leveraging the scalability, flexibility, and innovation of cloud services, organizations can accelerate digital transformation, drive business growth, and stay competitive in today's dynamic market landscape. However, careful planning, execution, and ongoing management are essential to maximize the benefits of cloud computing while addressing security, compliance, and performance considerations effectively. Thanks for being part of this learning journey. If you're looking to connect with other students, join our online community forum. There, you can discuss the course material, ask questions, and share your progress. See you there.